Hi, welcome second and third grade. I'm Mrs. B and we're going to talk about science. Before we get started, let's make sure we have our senses ready to go to pay attention and observe what's around us. Let's do a quick review of our 5 senses. Our sense of touch, our sense of hearing, our sense of smell, our sense of taste, and our sense of sight. Okay, let's look at some examples here of matter. Remember, matter is anything that takes up space and has mass. I'm made of matter, you're made of matter. Everything you see around me here is made of matter, and everything you see around you is made of matter as well. So here are some examples of matter. And what we want to explore today is what happens when we add heat to matter. And I want us to go through each of the examples and make some predictions about what might happen when we add heat. The first example here is a list of food items. What if we mix together milk, eggs, flour, sugar, maybe some extra things as well, and we add heat to it? What do you predict would happen? And when I talk about heat, heat is a type of energy that changes the temperature. So if I take these mixed items, food items, and then maybe I put them on the stove, I put them in the oven, what could we get? Well, I'll tell you what I would like to get. I predict that I will get a cake. I'm going to draw a cake. If I mix these things together and put them in the oven and add heat to them, I predict and hope that I will get cake. How would you describe these things before we added heat to them? Milk, a liquid, flour, sugar, solids. The egg is a mix. The shell is a solid. Inside the egg yolk is more of a liquid. So there are states of matter that we're going to review as well, but we can see each of these individual things. We can use our 5 senses to describe each one. And what it looked like before we added heat is very different from my prediction of hoping to get some cake. What about a piece of wood? How would we describe a piece of wood? And here's one example I have. We could describe its shape. Looks like a really tall triangle. It's smooth in some parts, but I could probably get some little pieces to come out of this as well. And so what happens when we add heat to wood? And what kind of heat could we add to this? Maybe we have a wood stove and we add this to a stove. Maybe we have a fire pit. Maybe we have a fireplace. Maybe you have one, you've seen one. So what happens to wood when we add heat to it? What do you predict that you would hear, smell, see? I predict I would hear maybe the wood crackling. I'm going to write down. I would hear crackling. What might I smell? Have you ever smelled wood burning? What does it smell like? How would you describe it? I would see wood burning. I would smell smoke. I would see smoke. So before we add wood to a fire or add heat to the wood, how different is that from after, based on our prediction of what we would hear, see, smell? What would this look like? Would the color change? How about a rock? And I have some rocks here that I just pulled from outside. And I'm trying to think if I have ever seen a rock in a fire. And maybe if you camp or you have a fire pit, there have been rocks in a fire, and you have an example of what that would look like. My prediction is that the rock, when we add heat to it, would still look like the rock that we started with. This one, I think, will be tricky. And I think I will see the same thing. I probably wouldn't hear a lot. And so I predict that I maybe wouldn't know if this rock was hot or not. And we need to be careful when we talk about heat and matter, because some things we might not be able to tell that it was heated. And I think a rock is an example of that. What about a crayon? Maybe you've never heated a crayon on purpose, but you've accidentally left some crayons outside, in the car, on a hot summer day. What do you predict would happen when we add heat to a crayon? I predict it would melt. And I'm going to do my best to draw a picture of what I think it might look like. I think the paper around it might look the same. So this is what the paper around it. But maybe this part's like oozing. It's melted. The wax has melted out. As we're thinking about heat and matter, what questions are coming to your mind? Let me give us some question starters. What is a what question that you have about heat and matter? What is a what if question that comes to your mind? What is a how question? A when question? And a why question. Let's review again what matter can look like. Matter can take the form of a liquid, a solid, or a gas. And I drew here some dots to represent that. So a liquid takes up the space of whatever container it's in. A solid keeps its shape. It wouldn't fill in whatever container it's in. And then a gas fills up the entire container it's in. And so when we were thinking about matter, maybe we need to think about what kind of matter, what phase of matter are we starting with? And then what's some evidence that when we start to add heat to matter, what is evidence or what is information that we can collect about this idea around heat and matter? And the best place to collect evidence is in the kitchen. And so I would encourage you to observe and see, hear, smell what's happening in the kitchen. Maybe you help with cooking in the kitchen. Maybe you see grown-ups around you doing the cooking. So what is some evidence that we know that heat has changed the matter? Because sometimes heat can change the matter and sometimes it can't. For example, when we're baking a cake or bread, we see the matter changes from the way it was before we added heat or put it in the oven or cooked it, and then after. When a crayon melts, it looks different from the way it was before. It's form-shaped. But when it cools, we can still use it as a crayon. The rock, though, my prediction was that the way it looked before, when we add heat to it, will still look the same. So sometimes heat changes matter and sometimes it doesn't. So some evidence that we've seen heat change matter is that there's a change in temperature. And if we had tools like a thermometer, we could measure the temperature. But if we can't get a thermometer, what are some ways that we can see or observe that the temperature has changed? Maybe the color changed, and maybe the color is red or orange. If it's really hot, maybe it's blue. Maybe we see steam coming from it. maybe its smell has changed. Maybe the things that we have before we make a cake smell very differently from when the cake is baking and then after we have a cake. So its odor, the way it smells changes. Its color can change. When we have a raw egg and we crack it open, if you've observed that, you see the yellow yolk and then you see a clear liquid or like a slimy gel kind of substance or matter around it. But when we cook the egg, it turns white, so its color changes. Maybe the shape changes, like the crayon example, and the form, again, like the crayon example. Or if we're burning a piece of wood, the wood we start with, and after we're done with our fire, then the form changes. So these are ways that we can know that heat has changed the matter. Another way we can show our learning around this when we're in the kitchen and making observations is that we can create a model. And with the model, we want to include some information to share our thinking and our ideas. We want to include a picture or a drawing. We want to include some symbols, key vocabulary, and we also want to include an explanation. Here's my example model of water. And I'm trying to explain what happens to water when we add heat to it. And here's one way that I'm showing you my thinking. So I'm observing before I heat up water, I see a clear liquid. I can see there's no heat. Then during, maybe I start to hear some bubbling. I start to see steam. Maybe I feel heat coming from the pot that I'm near, from the stove. I added heat, and then I still see a clear liquid. And then after, when there's no more heat and the water is starting to cool, I still see a clear liquid. There's no heat now, and maybe I still see some steam or gas. It might take a while before I stop seeing the steam or gas, and I would also notice that I could have less water after I boiled it than when I started. So what are things in your kitchen that you observe all the time, every day? Maybe you're a helper, maybe you do some cooking yourself, maybe you see the grown-ups around you. Let's think about what's happening before, during, and after some heat. Maybe you use a microwave and you heat up some of your food. What do you notice before, during, and after you microwave it, after you add heat? And what are other ways we add heat to matter in the kitchen? We have the stove, which could be gas and we could see the flames, or it could be electric and maybe we need to wait and see for the stovetop to turn red. We can also maybe have a microwave. Maybe we have a fire pit and we cook some hot dogs on there. Maybe we've been camping. What are some ways that you've seen heat added to food? What are some things that you've observed where heat's been added, but it really didn't change? So again, we need to be careful when maybe we have a sense or an idea that something could be hot, but it doesn't look hot. We have no evidence. We need to be careful when we pick up items like that. For example, cups and glass. So whenever I make hot tea, if someone else doesn't know that I made hot tea and they want to pick up that cup, there's no sign, maybe there's no steam, but the cup is hot. So we need to pay attention to that. I also included some drawings. So I wanted to show, this is a picture of a pot with some liquid water in it. And so in order to show my water, it's not close together like a solid would be. It's not completely filling up the space inside of the pot and around it like a gas. So I wanted to show a liquid does take up the space of the container it's in, and there is no heat. Then in my next picture, during, I added heat, and this is the way I used my drawing to show heat. What are ways that you would draw heat? Then I start to show that I have a liquid, but then some gas is starting to appear, and I can observe that there's some steam. And I used these wavy lines to represent steam. And then I also used a symbol for I used the letter T to represent temperature, and then I used an arrow to show an increase in temperature. I could have written the words out. I can use symbols. And then lastly, when I'm letting the water cool, I don't have any more heat. I still have some liquid, but I hope you can observe that I have less liquid than what I started with. I still have some gas in the form of steam with my wavy lines. So there's so much going on in our kitchens all the time that have to do with science and matter and heat. And I encourage you to take the time to make these observations. What do you see before, during, and after? And how is heat changing or not changing matter? Until next time, I hope you have a great day.
Welcome, mathematicians. I'm Miss Obenshane, and you're with APS at Home. This morning, we're going to do some counting, and we're going to use this 200 chart to help us. The first thing that we're going to do is count by tens, just to kind of get warmed up, right? So we'll find 10 on our hundreds chart, which is right here, or 200 chart. And when we count by tens, that means we're just including all of these numbers already in our 10. So if I say 10 and then 20, it's like I've included all these numbers and I'm jumping to 20. So count with me. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 200. Do you notice how this pattern just starts over again once we get to 100? It just has a 100 included with it. There's the 10 and the 20 and the 30 and the 40. So as we're doing this counting today, just be paying attention to the patterns that are there, and that will help you catch on to the pattern and the counting sequence. We also want to count forward, counting by tens, but we need to sometimes count backwards. That will help us with subtracting. So let's try counting backwards from 200 by tens. Count with me. 200, 190, 180, 170, 160, 150, 140, 130, 120, 110, 100, 90, 80, 70, 60, 50, 40, 30, 20, 10. We can also count by tens, but start at different numbers. And that also sometimes helps us when we're doing some mental math, adding tens from different numbers. So let's start with 6 and count by tens starting at 6. Count with me. 6, 16, 26, 36, 46, 56, 66, 76, 86, 96, 106, 116, 126, 136, 146, 156, 166, 176, 186, 196. Do you see that pattern repeat itself again? This same pattern that we have here. As soon as we get to 100, 6, there's the 16 and the 26 and the 36 and so on. So that pattern again just repeats itself. We could also start at any number, right? So let's try starting with 35. Sometimes counting by 10 starting at numbers with 5s in them can be confusing because you're so used to going 5, 10, 15, 20. And we're not counting by 5s, we're still counting by 10s. So make sure you're skipping a 10. So 35, 45, 55, 65, 75, 85, 95, 105, 115, 125, 135. We'll stop there going through that sequence. Let's pick one more and practice going forward and backward on that one. How about 69? So I'm going to find 69, and when we're working with a 200 or a 100 chart, right, I know that 69 is going to be in this row that all the numbers start with 6, and the 9 is going to be at the end of the row. So that can help me locate numbers on a hundreds chart. So 69, count with me, 79, 89, 99, 109, 119, 129, 139, 149, 159, 169, 179, 189, 199. Let's try it backwards now. Are you ready? 199, 189, 179, 169, 159, 149, 139, 129, 119, 109, 99, 89, 79, 69. Nice counting. Next, we're going to try it, and I'm just going to use this arrow, and the hundreds chart will be here in case you need to look at it, but we're going to try to just do it without having to point to the numbers and see if we can keep the pattern going. If I have an arrow going up, we're going to count forward. If I flip it around on you, then I want you to count backwards by tens from the number that we're on. All right, so let's start with 33. So 33, and we're counting by tens forward because the arrow is going up. 33, 43, 53, 63, 73, 83, 93, 103, 113. Oh, I switched it around. We're going to go backwards. We were at 113. So 103, 93, 83, 73, 63, 53, 43, 33. Nice counting. So you can practice doing this with a hundreds chart if you print one off our website, or you can just think about those number sequences and just try to practice them orally, counting forward and backwards by 10 from different numbers. Since we were talking about how to find numbers on the hundreds chart, we're going to come over here and look at this. I have some pieces of the hundreds chart, and when I printed them out, the printer went crazy, and there are numbers missing everywhere. Can you believe it? So we're going to have to figure out what numbers are missing. Let's look at this first one. I have 46. Remember, we said if we're going this way across there, we're counting by ones. 1, 2, 3, 4, 5, and that happens in every row, right? If we're going this way, we were just practicing counting by tens. So if we see 46 here, what number is going to be in front of the 46? It's still going to be a 40, right? And 5 is in front of 6, sorry. So we're going to have 45. That would be in front of 46, right? What would be below 46? We'd be counting by tens to do that. 46, what comes after the 40s? What do you think? That's right, 50. And it would be 56 because we're in the same column. Now we've got this row, and this would be pretty easy, right? We just have to count by ones. 56, 57, 58, right. And now let's see if we can use some of that backwards counting to help us up here. So we have 56, 46, 36, you're right. And then 26. Nice work using your counting by ones and by tens. Let's try this one over here. We have 63. These are all in a row, so we're just going to be counting by ones, right? 63, what comes after 63? 64, yep. 65. Now we can try going backwards. 65, 64, 63, 62. And then 61, right. Now we've got to work on some tens, right? 64. What comes after the 60s? The 70s. 74, 84. You are pretty quick with this. We got a couple more puzzles that we'll try. Oh, this puzzle right here, we have the 90s row, which means that we're going to get into the hundreds row like here below it, right? So 94, what comes after 94? 95, 96. Now I have to count by tens to get any of these above or below it, right? So 96, what comes after the 90s? 100, you're right. And then we have the 6. So 106. And then 116, yep. And then over here, we're gonna have to count backwards by tens to figure these out, right? What's before the 90s? The 80s. So 94, 84, 74, 95, 85. You are pretty clever with these hundreds chart puzzles. How about this one right here? It looks like a backwards L, doesn't it? I think that might mean there's going to be a lot of backwards counting on this one. 78, we'll go by ones first. 78, 77, 76, that's right. Now we've got to go by tens, right? Before the 70s, 60, 68, 58, and 48. I'll let you just look at that one right there, and we can work on that at another time. But there are some puzzles, more puzzles, that you could download off of our website if you want to practice this, and also a document that has 1 to 1,000 in it if you want to try some puzzles or some working on counting higher than what we worked on today. Next, Ms. Gaudet is going to come in and do some problem solving with you.
Hello, everyone. So last time we were together, we were working on Carol's numbers. And we were thinking about how to place these numbers on the number line and what was our reason why we placed them there. So let's review what we did last time, and then let's go ahead and finish off the puzzle. Reminder, you can download this off of the website, get it, and then do the work with us. Or if you have a pencil and paper, do the work with us. Again, as we're going through, before I give an answer, pause me, try it out yourself, and then check your work as you're going through. That way, you're not just I'm not just giving you the answers. You're actually trying to think through the math. And remember, what I'm doing is what I call teacher talk. So I'm trying to show you how I would solve it. But remember, our best learning is if we attempt it our first and then look at how someone else solved it and try to think and reflect about it. Okay, let's get started. Last time, we talked about what the largest three-digit number we could do, and we talked about what was the smallest three-digit number we could do. So we came up with 742, and we talked about how we knew that, the individual digits, how that would help us. Our smallest number we came up with was 247. Again, looking at the digits. Then we had to, it was here, about where would 85 be on the number line. We went ahead and placed it here, since the only thing that the number line had for us was this 42. This is a good example of the original number line. Then it asked, and I forgot to, did you guys notice that? I had forgotten to mark up what was I supposed to be doing last time. So let me go ahead and fix that. I knew I had 85, and it says about where. So, and then the next one, number 4, it says about where would 21 be? And we had talked about that we noticed 21 was half of 42. So we went ahead and placed it about the halfway point on our number line. And we had talked about 85 was about twice as more, double 42. Not quite, but about. And that's where we left off last time. So let's go ahead and get started on this time. Again, remember to pause me, try it on your own, and then go ahead and watch and think about that. So number 5 says, about where would 31 be? So what is our quantity? 31. And then what are we being asked to say, to do? About where? So if we were to look at our number line, about where would 31 be? Do you have an idea? Okay. All right, so let's go ahead and look. It's 31. Well, I know 21, if I counted by tens, that Miss Obenchain had talked about, that it would be just 10 more. Maybe 21, 31, 41. Oh, there we go. There's our 31. And then the last thing we have to do is tell Carol how you knew where to place 31. So my quantity was 31. And then I had to tell how I knew it. All right, so let's go ahead and write that up. So we were talking about 31. So let's go ahead and write that out. 31 is placed there because it, and remember it is 31. Anytime you have something like this, you want to make sure to tell what it is. It's 31 is almost in the middle of 21 and 42. And some of you may have said, oh, well, I counted by tens, 21, 31, 41. That's fine too. I thought about it as doubling, halving, middle kind of thing. All right, so that is Carol's numbers. The next activity we're going to be doing is called the wheel shop. We're going to revisit the wheel shop. And in this one, please remember to go ahead and download it so that you have it, or you can just go ahead and work with me on your own sheet of paper. But again, we're always working together and not just watching. You're trying to do the math with me. All right, so here's the wheel shop. You go to a shop that sells tricycles. There are 18 wheels in the shop. How many tricycles are there in the shop? And then explain how you knew. So the first thing we do is we do our quantities. So this one's easy, 18. But what other quantity do we have in there that is not explicit for us? Did anybody think of the tricycle? Because what does the word tricycle mean? It has 3 wheels, so that helps us out. That is a quantity also. Then what do we have to solve? How many tricycles? And then explain. So let's go ahead and let's get into our work. Oh, it's right here. I'm looking around for my paper and it's right here in front of me. So let's go ahead and look at it. How many tricycles would I have? How could I do this that would make it easy? Some of you said, oh, I could just easily do a division problem. Perfect, try it out. Some of you are looking at that like, no, that might not work. It's okay. I'm going to show you how I thought about it. So, remember, did you pause and try it on your own before you're having me work through it? Good. All right. So I did it this way. I knew a tricycle has 3 wheels. How many tricycles is that? Just 1. So I'm going to just keep going until I've hit the 18 wheels. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So, how many wheels, let me rephrase, how many tricycles are there? Did you see it? 1, 2, 3, 4, 5, 6. So then we would go ahead and explain how we knew that. If you did a division problem, explain how you knew that division problem was the answer, 6. If you did it something like I did, explain how you knew, prove to me that that works. All right, we're going to be moving on to Miss Sears and, no, Miss Carnes. I'm sorry, I just saw Miss Sears. So Miss Carnes will be working with you next. Have fun, guys.
Hello and good day, mathematicians. Miss Carnes here with you today, and today I'm here to read a book to you. This book is called Betcha, and it is by Stuart J. Murphy, and it is a Harper Trophy book. So guys, I want to tell you that this book is all about estimation. And estimation is a really valuable skill. So when we estimate, we are trying to make an educated guess about how many there are of something. Not a random wild guess, but a guess based on some things we know about numbers that can help us. So let's go ahead and read about how this character, the characters in this book, put estimation to work. I think we'll sit for this part. Okay, Betcha. Hey, look at this. Planet Toys is having a contest. Whoever guesses the correct number of jelly beans in the jar in their window wins 2 free tickets to the All-Star game. Oh yeah? Well, let's go down and check it out. Sounds like a pretty good prize for guessing how many jelly beans. I bet you I can win. Oh yeah? Well, I'm really good at figuring things out. I bet you that I'll win. I wonder who will win this bet. If you're so good at figuring things out, can you tell me how many people are on this bus? Yeah, you betcha. Oh my gosh, you guys, he can't do that. There is a lot of people on that bus. How is he gonna guess how many and get close? Do you have a way that you might think about it? Let's see what his way is. All right, how many? Well, he's looking at the rows. 4 people sitting this way, and there's 10 rows. So about 40 people plus a couple people standing up. So I betcha about 43 people. Think he's right? 1, 2, 3. His friend is counting. 42, 43, 44, 45. I just counted and I got 45. I was pretty close, says his friend. He was pretty close. That was a good estimate and a good strategy for getting it. Wow, look at that traffic jam. I bet you can't tell me how many cars are stuck on the block. I bet you I can. How the heck is he gonna figure that one out? That's a lot of cars. Well, let's find out. Go ahead and try, says his friend. All right, well, there's 4 lanes of traffic, and there's about 6 cars in each lane on the block. So I bet you about 25 cars. Wow, I wonder if that was a good estimate. All right, counting to double check. 1, 2, 3, 4, 21, 22, 23. I counted 23. Huh, I was almost right. Here's a store. Look at all that cool stuff. About how much do you think it would cost to buy it all? I bet you I can tell you how much. That's a really good skill to have to figure out about how much things are gonna cost. Go for it, his friend says. Well, rollerblades, almost $40. Walkie-talkies, just over 20. That equals about 60. And 60 plus almost 30 is about 90. And then 90 and a little more than 10, about 100. I bet you about 100. Wonder how close he got. Let's see. His friend is adding up all those numbers to get the exact answer. I get 101. See, I was close again, and I didn't even need a pencil. He is a really good estimator, isn't he? Okay, now for the real thing, about how many jelly beans are in the jar. This is the contest, right? Remember they wanted to try? So his strategy here, he thinks about layers of jelly beans in the jar. So he thinks the top layer, he divides it into 4 sections, and he thinks there's about 20 layers like that in the jar. So about 10 in each section on the top. So each section would have 10. And 4 sections, 20 layers. 40 times 20 is about 800, plus a few at the top. I bet you about 810. Well, I can't count them, and he's been pretty close every time, so I'll just add a few to his number. 812 is the guess they put forth. Incredible! That's exactly right. You're headed to the All-Star game. Wow. Betcha I know who wants the other ticket. And the 2 friends get to go to the game, thanks to excellent estimation skills. Let's spend just about our last minute taking a look at some of the strategies that were used here. Oh, am I on this one? Yes. All right. So, thinking about the bus and the traffic lanes, he used kind of like an array structure. Arrays can help us organize and think about how many we have. So he thought about 4 lanes of traffic, remember that? And about 6 cars in each lane. And then he pictured, right? Pictured those in an array. So there's one row of 6 cars. Two rows of 6 cars. I'm hurrying, my array is a little sloppy. So we're at 12. And we continue to build our array. Oh my goodness, Ms. Karnes ran out of sticky notes. So far we have 3 lanes of 6 cars, 6, 12, 18, and if we added our last row of 6, we would have how many? 24 cars, and he guessed 25. He was really quick. The other thing I wanted to look at was how he estimated the amount that items would cost. Here were the actual numbers he had. $39, $22, $28, and $12. He changed all these to friendly numbers. 39 was about 40, 22 was about 20, 28 was about 30, and 12 was about 10. Which set of numbers looks easier to put together? I'll betcha you're saying this one. 40 plus 20 gets us to our 60. 60 plus 30 gets us to 90, and 90 plus 10 gets us to 100. And if you remember, the actual answer, if we added all these up exactly, was 101. So we learned that if we are thinking about counting a very large amounts of things, sometimes we don't have to get an exact number, but we can use what we know about numbers. We can use what we know about how things are arranged, like lanes of cars, and that can help us to think about how many there are. Thanks, guys, for listening to this story with me, and I'm going to turn it over to Mrs. Sears.
You're going to need to stay with me for a few minutes.
I get to play a game.
Yes. You know, I'm thinking about that estimation, and it kind of reminds me, just in the sense that I see the game that we're going to play is all about going over a hill. It's actually called Over the Hill. And for those of you who might have thought about estimation as, you know, trying to get over a certain number to know that you're either going to go roll down the hill to go to the lower number or roll down the hill the other direction and go to a higher number. That's kind of the connection that I make with this, but it's not necessarily the way that the game is played. So let's talk about how it is, okay? So what you're going to need to know and just you're going to have these directions that are available on our APS distance learning website. It's going to give you the directions. It's also going to tell you what kind of materials that you're going to need. You are going to need 3 dice. So you can share these 3 dice with somebody at home. I chose to go ahead and just have 3 dice for you and 3 dice for me. Or if you needed some numeral cards, you can do numeral cards 1 through 6 because we know there are 6 sides on the cube or on the die. So that would help you kind of figure out how to do that. The other thing that you're going to want to do is you're going to want to roll these 3 dice. Okay, let me explain how the game works. So you notice there's something on our over the hill chart. Our over the hill chart has 1 all the way through 18. You have to be able to add or subtract the 3 dice, to manipulate those 3 dice in any way, but you have to be able to cross off those numbers in numerical order. It's a little bit of a twist, okay? You don't have to use all 3 dice at one time, but you do have to use the combinations of the 3 dice, either adding or subtracting, to be able to get those numbers in numerical order and go over the hill.
Mrs. Sears?
Yes.
Can I reuse dice? Like, can I use one number more than one time?
No. So if there comes a point when I can't go any farther, like if I am having trouble just even getting a 1 in this first roll, then it's your turn. I've lost my turn.
Okay.
If there's no combinations that I can make that will make me get a 1, you're going to have to start with your turn. When it fails to get any combinations to go in numerical order to the next number, then that is the end of your turn, but you're trying to get to 18 first, okay? That's the goal. That's the attempt. All right, are you ready to begin?
I'm ready. I'm excited. These
Okay.
guys have been playing games, and now I get to play a game too.
I feel a little over the hill, just that I'm over the hill anyway. You know, you guys are a lot younger at home. Sometimes it's hard going over that hill. All right, I have a 4, I have a 3, and I have a 5. So how this would work is I would do the 5 minus 4, and I'm going to go ahead, and you should have a marker over there. 5 minus 4 is going to let me mark off that 1. Okay. 5 minus 3, because I can use these, remember, in any way I can. 5 minus 3 would be a 2. And I don't think I'm going to be able to go any further, because if I added 5 and 4, that's like 9. If I added 5 and 3, that's 8. That's not going to get me any further. I have to get something that's going to make adding or subtracting with that 5, 4, and 3 to be able to get to a 3. I can't just take the 3 by itself. It has to be with another die. Okay.
All right. Here we go. Okay, so I get a 1, a 3, and a 3. Can I use my 1 by itself?
I'm wondering, I think no, you can't use your 1 by yourself because I had a 3 and remember I couldn't use that by myself. But I'm thinking you could probably use all 3 of those combinations, all 3 of those dice. You just have to add and subtract.
I see. So, thank you for that clue, Mrs. Sears.
I'm being nice. I could probably have done some competition there.
Yes, she's being very nice. So, my clue then is that I'm going to add together, or actually, I'm going to subtract 3, take away 3, and that leaves me with 0. But then I can add back on my 1. So at least I get a 1 and I can cross that 1 off.
Perfect. But I think you got another one there too.
I do?
Yeah.
Oh, goodness, I do. So I can also take one of my 3s and subtract 1, and that's going to leave me with 2. So I get to cross off the 2 as well.
All right. Now she can't go any further because we would have to have a 3 next, right? So that 3 had to be gotten some way other than just being able to have it like laying there on the dice. All right. Let's see. Let me try. Okay. I have a 6, I have a 5, and I have a 4. Let's think about this. Could any of those get me a 3? 6 and 5 is 11, minus 4 is 8, nope, so 5 minus 4 would be 1. Let's see, plus 6 would be 7. I don't think I have a solution to how to do that. I'm trying to think about it. So 6 minus 4 would be 2, plus 5 would be 7. I think I have just too big of numbers to be able to go and find that 3. So I'm going to lose my turn.
Oh, I was thinking about it too, and I didn't see any ways either. Okay, so this time I have a 1, a 2, and a 4. So first I have to be able to mark off a 3, and I can do that by taking 4 and subtracting 1. That gets me my 3.
You could have done 1 plus 2 as well.
I could have done 1
She has a
plus
1
2 as
and a
well.
2 there. I wish I would have gotten those good numbers.
I had more than one way to make 3, didn't I? Okay, and then let's see. Can I make a 4? 4 and a 7, no. I don't see a way to make a 4.
I don't see a way either. I'm looking for it as well, and I don't see a way. She has a 1, a 2, and a 4. We're trying to make a 4.
Oh, darn.
And you just can't take the 4. You have
Too bad.
You have to do something with the adding and the subtracting. All right.
Sears' turn.
All right. So I have a 4, a 2, and a 3. So let's think. I really, really need that 3. Okay, maybe if I added 4 and 2, that's going to give me 6. Minus 3 is going to be a 3. So I am there. Let's see if I can figure out how to do a 4. Man, if we could multiply, that would help too, but 4 and 2 is 6. Let's see, 4 minus 2 would be 2, plus 3 would be 5. 2 and 3 is 5, 4, 9. I think I'm stumped again. I can't get that 4 out of what I have.
You were so close.
We're getting little inch by inch. I'm not going to make it over the hill yet.
Okay. Wow, and I'm rolling all. This time I rolled 3 2s. Okay, so I can definitely make a 4, right? By using my doubles and putting together 2 of those 2s is going to give me a 4. But a 5.
5's going to be a hard one because those 2s are all even.
Yeah, I don't see a way for me to use my 3 2s in any way to get a 5. So, Mrs. Sears?
My turn.
Your turn.
All right, let's see how much further we can get. Okay, I have a 1, I have a 2, and I have a 4. And I need a 4. Let's see, 2 and 1. Oh, gosh, if I would just be able to use those, some would be really good for the next one. 2 and 1 is 3, 2, 4, 1. I don't think I'm gonna have a way to do that.
Oh, darn.
Oh no.
This game's a little harder than we thought, right?
Yeah, definitely. Maybe we should have just gone to 10.
Okay, so this time I got a 5, a 3, and a 1.
All right.
Okay, so.
I don't know if we're going to be able to finish this roundup because I think we're
No.
about out of time.
We are out of time.
So just remember that you can find all these materials at the At Home with APS site, and you can even change the variation, maybe not go to 18. This took us a little bit longer than we thought. But we've certainly had a good time, and I'm glad we've had a little bit of competitive thinking in the way that we were working. And we really want to thank you guys for joining us today with At Home at APS. Bye-bye, mathematicians.
Bye, guys.